recording. Okay. So today I'll just start some basics of topology as I promised. So firstly I'll be teaching about the concept of metric spaces. Metric spaces. So I'll be giving some definitions and examples regarding metric spaces. So far okay, so we basically have a set, right? Set is basically a fundamental object in mathematics, and on this set you basically define a map to real numbers. So this particular map, which takes an element from the set and another element from a set and gives out a real number, and if it satisfies the following properties: d of x comma y is greater than 0 for all x comma y in x, and if distance of x comma y is equals to 0 if and only if x is equals to y, and distance of x comma y should be less than or equals to distance of x comma z plus distance of z comma y for all x, y and z belonging to the space. So once you have a set and you have a notion of distance d, then this is called a metric space. So for example, I'll talk about a discrete metric space. So basically I have a set of natural numbers n, I have a set of natural numbers and I define distance between the natural numbers this way: d of x comma y equals 1 if x not equals to y, and 0 if x is equals to y. So this is an example for the metric space. So take two numbers 1 and 2. So what is the distance between 1 and 2? According to this particular formula that I have defined, it's 1. So what is the difference between distance between 1 and 3? It's 1, because if 1 is not equal to 3, hence the distance between them is 1. So distance between 1 comma 1 is 0. So is this a valid notion of distance? So I have given 3 axioms, right? Let's check them. So is d of x comma y greater than or equal to 0? If it is 0, implies x is equals to y. So by the way we have constructed this matrix, from the way we have constructed this distance, it satisfies this axiom. So is distance of x comma y equals to x comma z? Yeah, this is true. So now let us check the third axiom. So d of 1 comma 3, which is equals to 1, which is less than or equals to d of 1 comma any natural number, that is, say any natural number, arbitrary natural number x, plus d of x comma 3. So if x is not equals to 1 or not equals to 3, this is 1 plus 1, so it's greater than 1, so it's anyway satisfied. If x is 1, this is 0, this is 1, so equality sign is there. X cannot be both 1 and 3 at the same time. So this is a valid notion of distance. in a metric space. So this is called a discrete metric space, which you basically apply in many of your neural network algorithms later on. So now if say a set basically obeys some vector axioms, vector space axioms, and we define a map norm from X to R such that it must satisfy these axioms. If norm of X equals 0, should imply X is equals to 0 belonging to the vector set X, and next axiom is norm of X plus Y is less than or equals to norm X plus norm Y, and norm of alpha X equals mod alpha into norm X in the vector space X. So these are three axioms of, three definition of distance, and once you have this, you have a normed vector space, and you can generate a metric from the norm, which will be called as metric induced by norm. If you define d of x comma y to be equals to norm of x minus y in X. Okay. And further we have another notion. We say that the metric defined is basically it is invariant of translation if d of x comma y equals d of x plus a comma y plus a for every a belonging to the vector space X. Okay, so this is a metric space generated by the vector norm. So some examples. So your set of real numbers is basically a vector space and also a metric space induced by the modulus norm, where basically d of x comma y, distance between two real numbers, is basically equals to the absolute value of their two numbers, difference of the two numbers. So this is a vector space with a metric induced by norm. So let us say we have continuous functions c of 0 comma 1 comma, we induce distance this way b. So a function f belongs to the continuous set of functions, and let g belongs to also the continuous functions, and we define the distance between f and g to be equals to integral of 0 to 1 mod of f minus g d some measure. So this is another vector space. So one classic example is Rn. Rn is a vector space of n, and we can define a p norm on Rn where say x belongs to Rn. So you can write this as x equals x1, x2, so on till xn, and norm x of p equals sigma I is equals to 1 to n mod xi whole power p whole power 1 by p. So where the distance between x minus y in Rn is basically sigma is equals to 1 to n norm xi minus yi whole power p whole power 1 by p. So if p is 2, this is something called Euclidean distance, something that you have heard of. It is basically sigma xi minus yi whole square whole power half. So these are some examples of vector spaces and this thing. So this is basically the starting point of topology. So we are basically have introduced how to define the notion of distance on a set. Later on we'll show so basically we need to show that we need to introduce the notion of distance to show that how elements are converging actually. So convergence again comes here, how elements are converging and so on and so on. How or if a function is also if a function is continuous or not, to check that you need this notion of distance. Okay, so this is a basic introduction of topology. We have introduced the notion of a set and how to introduce distances on a set, and later on we'll go with things. Okay. So now let's go to distribution, the PDE part. So last time we have shown that the map F and the distribution defined on TF is basically a bijection. Let's proceed with some examples of distributions. So just recapping. So omega in Rn is an open set, and d of omega consists of all such functions such that they are infinitely differentiable, and support of f is compact. And the convergence in this part, the topology that we have defined on TF, d of phi is like if phi n converges to 0 in d of omega, what does it mean? It means that all the derivatives phi n dash should uniformly converge to 0. So this is what convergence means in this particular metric space. So the first example of a distribution. So what's it? I mean, okay. So just to recap the distribution, the definition of distribution. Basically, distribution T maps from d of omega to R implies T belongs to the dual space of the set we have defined, and that is T is basically a bounded linear continuous map from d of omega to R. So basically it's a dual space of d of omega. Okay. This is something that we have defined in our last class. Okay. So the first example of a distribution is this. So we have f belongs to L1 locally integrable function. Then we define Tf from obviously from d of omega to R such that T of f of phi is nothing but integral over r f into phi dx. So this is an example of a distribution. So basically this is a bounded linear map. Tf of phi should be less than or equals to norm phi of infinity, because it's a continuous function, into norm f into L1, because say this should be over support of phi, because support of phi is compact, so f is basically locally integrable function. So this is a bounded linear map, and if phi converges to 0 and all the derivatives of phi converge to 0, implies integral f phi dx, which this also converges to 0. So this is our first example. The other example is something that all of you know, kind of you have studied in your electrical circuits and everything, but you have not seen it in this way. It's a Dirac distribution. So for every x belongs to Rn, delta of delta x is phi of x. So it is basically evaluation at that particular point. Just a fact that I'm going to state without proof. You can't generate Dirac distribution from a locally integrable function. So there may not be f in L loc of 1 such that integral of f phi d mu equals delta of x of e. There may not exist such f. So you can't generate a Dirac delta function from some locally integrable function. Just a fact. I have written down the proof in notes, but I am skipping because it kind of requires mathematical rigor that we engineers may not require. So basically I am trying to get over some definitions as quickly as possible so that we can start the main juicy stuff of PDEs, such as finite element methods and finite difference methods and convergence simulations and so on. That might help you in your neural network thing. Okay, now I'll just show some operations on distributions. So let omega belongings to Rn be an open set, and we define a multi-index order n of tuple such that alpha 1 so on till alpha n is such that each of the alpha I is greater than 0 and alpha belongs to some integer z. So we define mod alpha to be alpha 1 plus alpha 2 plus so on till plus alpha n, and alpha factorial as basically alpha 1 factorial, alpha 2 factorial and so on till alpha n factorial. So we have d alpha equals dou of mod alpha by. So this is the first time you might be waiting to see a partial derivative, and this is how voila it comes. Dou x alpha 1, dou x alpha 2, so on. So what this basically means is that if n is 2 and alpha is 2 comma 1, so d alpha is basically dou 3 by dou x1 square into dou x2. Similarly, if we choose alpha is equals to 1, 0 and 2, implies d alpha is equals to, just add these 3 by dou x1 dou x2 square. This is basically how we compactly write our derivatives. Okay. Now f belongs to C1 of R. So we basically try to find derivatives of our distributions. Tf dash of phi. These are basically some change of integrals. That's it. F dash of phi dx, which is equals to minus integral of f phi dash, which is equals to minus tf of phi dash. Basic order of change, just changing the order of integration. So if t belongs to d1 of omega, we define td dash of such that t dash of phi is basically equals minus t of phi dash. So this comes from the above expression. Similarly, t double dash, if this belongs to d double dash of omega, you have t double dash of phi, which is equals to minus of t of phi double dash. So tn of phi is basically minus 1 power n t of phi. It's a derivative on distribution. So let us try to find the derivative of the Dirac delta distribution. Okay, so delta dash of phi is equals to minus of delta of phi dash by the relation, which is equals to minus of phi dash of 0, which is equals to Dirac dash of phi. This derivative of Dirac distribution is called dipole distribution. This also cannot be generated by any measure. Okay, now I'll just show that. Now let us go for Heaviside function. H of x equals 1, 0, x greater than or equals to 0, x less than 0. T dash of h of phi is basically equals minus th of phi dash, which is equals to minus integral h of phi dash. Again, you can basically change the integral and you get this is to be minus of phi dash of x on the 0 to infinity, which is equals to phi of 0. So what you basically get is th dash of phi is basically phi of 0, which is equals to Dirac 0 of phi, implies th dash is equals to delta of 0. That's how the delta function and the Heaviside function are connected. But t of h dash of phi is basically integral. The derivative of the step function is 0 almost everywhere. Phi into dx is equals to 0. So t dash of h is not equals to th dash. Okay, sorry. It's like saying a is not equals to a, so it's upside. So you have derivative on the upside. Here the derivative is down. This may not hold. Kind of a disturbing thing, but let's proceed further. But this does not hold for any arbitrarily L1 function. So we just go forward and check the result for any arbitrary functions. I mean, we prove this claim that the particular equality holds for the continuous functions. So if f is continuous, on a comma b subset of R, then t f whole dash is equals to tf dash. So I will prove this. So f is absolutely continuous on a comma b. So say phi belongs to some compact d of minus m comma m less than m. So because f is absolutely continuous and support of phi is subset of a comma b, so let us define this particular area a of all x comma y belongs to R2 such that minus a less than or equals to x less than or equals to y less than or equals to a. Basically this square. This is the area of that. So we define, okay. I define this integral on that particular domain. I is equals to integral a phi dash of x and f dash of y dx dy. So we just interchange the limits. So basically the first integral that we get is minus a to a f dash of y into integral of minus a to x of phi dash of x and dx dy, which is equals to minus a times a f dash of y into phi of x. Phi is compact on minus a to a, so we get this to be phi of y. Sorry, this is y. It's y dy. So this is our first integral. And second integral, firstly, so we have firstly integrated this with respect to phi, then we have integrated the entire term. So now we integrate now with respect to phi dash of x minus a, this is basically x to a, right? X to a times f dash of y dy and dx. So you integrate this, so you get minus a to a phi dash of x into f of a minus f of x dx, which is dy f of y, which is equals to f of a times minus a to a phi dash of x minus integral minus a to a phi dash of x f of x. I'm writing in a corner. I'll write this step again. I'm just integrating this, and after integrating this particular element, you can do this slowly. I have the recorded thing. So you basically get minus integral minus a to a phi dash of y f of y, but both the integrals are the same. Hence this is equals to minus a to a f dash of v phi of y dy. So this is basically a distribution on f dash, which is equals to minus t times f times phi dash. So you basically have tf dash is equals to minus t f of phi dash. So for the continuous function, this particular equality holds. Okay, so I'll just prove one last result for today. So this is something that I'll just directly write the result. I won't prove this. If f is differentiable function, f is differentiable, okay, and t belongs to the distributions, so it's dual space of d of omega. So implies there exists a constant, and if t dash is equal to 0, implies there exists a constant c such that t of phi is equals to c times of integral of phi d, where mu is the measure. Okay, so in today's class, I think I have stated the results and I went through things a little fast, but it's fine. It's just that these are some formal definitions that I have to define before getting into some good stuff. So I've done this kind of fast. So the next step is to go to finite element method, some approximation methods, and so on. So then we'll be seeing some good graphs and everything. So till we get in to apply to get good graphs, good stuff that we want, we have to go through this abstract part. Okay, I guess with that I'll end today's lecture. Okay, thanks for coming.